Welcome to This Explainer. Today, we're taking the abstract, highly complex world of physics and bringing it right into full view. We're going to initialize a holographic journey into the invisible web that surrounds, well, almost everything in our universe, the electric field.
It all really starts with this one core mystery, a question that actually baffled scientists for centuries. How do objects push or pull on each other without ever making physical contact? Think about it. If I want to move a coffee cup on my desk, I literally have to touch it, right? But charged particles, they don't. They exhibit this crazy action at a distance. They can repel or attract one another straight across the vacuum of space. And to understand how they actually pull that off, we have to visualize something that is completely invisible to the naked eye.
All right, let's boot up the simulation sequence for today. We'll start with 1, the invisible force matrix, move into 2, point charges and dipoles, then 3, simulating continuous charge distributions. Look at 4, deflecting particles and fields, and finally wrap up with 5, dipole dynamics and torque.
Section 1, the invisible force matrix, visualizing the field. So let's begin by defining exactly what this invisible web is that we're dealing with. An electric field isn't a physical push itself, not at all. Instead, it's an abstract property of space that's set up by a charged object. It's kind of like the underlying matrix that conveys the information for a force. To actually measure it, we use a tiny positive test charge, which physicists just call Q0. We place Q0 into this space and simply measure the electrostatic force acting on it. The electric field, E, is just that force divided by our test charge. It's basically the potential for a push or a pull, just waiting out there in the vacuum.
To really get a grip on this, we lean on Michael Faraday's brilliant concept of electric field lines. Think of these rules as the operating parameters for a glowing fluid that maps out the force. First up, the electric field vector at any given point is always perfectly tangent to these field lines. Second, where the lines bunch up really tightly, where their density is highest, that's exactly where the magnitude of our field is the strongest. And fundamentally, these glowing lines always burst outward from positive charges, and they terminate by sinking right into negative charges.
Section 2, point charges and dipoles, the building blocks. Okay, let's see how this builds when we drop actual charges into the mix. If we take a single isolated positive point charge and just drop it into our space, it creates this perfectly symmetric outward bursting field. Every single vector points directly away from it. And the math tells us that the strength of this field decays based on the square of the distance from the particle. It's a classic 1/r² drop-off, but things get a whole lot more fascinating when we add a second particle. Now here's where it gets super interesting. The rapid signal decay of an electric dipole compared to just our single point charge. A dipole is simply two particles of equal but opposite charge, separated by a really tiny distance. Because you've got a positive charge pushing outward and a negative charge pulling inward, if you step back and look at them from a distance, they almost look like they occupy the exact same space. They almost completely cancel each other out. But not quite. Because of this near cancellation, the field's magnitude drops off so much faster, at a rate of 1/z³. Section 3. Simulating continuous charge distributions, scaling up. Having mastered the building blocks of single particles and paired dipoles, we are absolutely ready to scale up. Because in the real world, objects aren't just 1 or 2 particles, right? We have macroscopic rods, rings, and flat disks coated in literally billions of charges. To map the field of these continuous shapes, we run a digital calculus protocol. We mentally isolate a tiny microscopic sliver of charge on the object. We call it dq. We find its tiny specific contribution to the total electric field, dE, and then we just add them all up. But wait, here is the ultimate hacker's shortcut. Instead of doing a massive, messy mathematical integration, we just look for symmetry. If a disk is perfectly round, any field vector pointing up from one side is perfectly canceled out by a vector pointing down from the opposite side. Bam! Symmetry literally does half the work for us. And this brilliantly illustrates our math out in the wild. This is an atmospheric sprite. This phenomenon happens when the electric fields generated by massive storm clouds get incredibly dense. When the field magnitude exceeds a critical value, specifically about 200 newtons per coulomb up in the thin air 60 kilometers high, the electric field literally rips electrons right out of the air molecules. This process is called electrical breakdown, and it creates these massive, glowing, high-altitude sprites. It is the invisible force matrix suddenly and violently becoming visible. Section 4. Deflecting particles in fields, action and reaction. So, now that we know how these dense fields are made and exactly how they behave, let's unleash some particles into an external field and watch how they react. When a moving charged particle flies through a uniform electric field, it experiences a constant force, which is defined by a beautiful, simple equation. Force equals the particle's charge times the electric field. F equals QE. A perfect everyday application of this is an inkjet printer. Tiny negatively charged drops of ink get shot between two charged plates. The downward electric field exerts a constant electrostatic force on the drop, perfectly deflecting its trajectory so it lands in the exact right spot on your paper to form a letter. The invisible field is acting as a precise, frictionless track.
Section 5. Dipole dynamics and torque, the electric dance. For our final simulation, let's take that electric dipole we built earlier, that paired positive and negative charge, and drop it right into a uniform external field. Because the external field is uniform, the positive end of our dipole gets pushed in one direction with the exact same force that the negative end gets pulled in the opposite direction. So the crucial takeaway here is that the net force on the center of mass is strictly zero. The dipole doesn't move forward or backward at all. However, because those opposing forces are acting on different ends of a rigid structure, they create a twisting force, a torque, and this torque forces the entire dipole to spin in place. The dynamics of this spin depend entirely on the dipole's angle relative to the field. It helps to think of the dipole exactly like a pendulum. When a pendulum is held totally upside down at 180 degrees, it has maximum potential energy and is incredibly unstable, right? If it's at 90 degrees, it experiences the maximum twisting force, or torque, pulling it down. But at 0 degrees, the torque drops to zero, its potential energy is at an absolute minimum, and it is perfectly stable. The dipole naturally wants to shed its potential energy and stably rest at 0 degrees, perfectly aligned with the flow of the electric field lines. It's just a beautiful, invisible dance.
We've spent this entire explainer mapping out the rules of static electric fields. We know how they originate, how they decay, and how they twist objects. But it leaves us with an absolutely incredible final question. If this is what a stationary, static field looks like, what happens if we take a charge and start wiggling it? What happens when these fields start continuously changing and oscillating? Well, a changing electric field actually induces a magnetic field, which in turn induces an electric field, and they continuously create each other, rippling outward through the vacuum at 299,792,458 meters per second. Those exact same rules we just learned today eventually give birth to electromagnetic waves. They give birth to visible light itself. But that is a simulation for another day. Thanks for joining me on this explainer, and keep questioning the invisible forces around you.